All right, hello everybody. Let's prove nice little theorem shows up in 4.5. Very, very common. In fact, some people even do this in high school, showing that root 2 is irrational. Now, this is actually a pretty big deal. It's the first time you actually get to prove that there are these things out there called irrational numbers, numbers that cannot be written as fractions. Okay? And of course, to show something is irrational, show something can't be done, the way we're going to prove it is we're going to assume it can be done and then get a contradiction somewhere. So the proof is by contradiction. Assume that root 2 is rational. Okay, so assume what I'm hoping for in terms of a contradiction. Now, when I assume root 2 is rational, now I got to write out what that means. So what does it mean to be irrational? It means it can be written as a fraction. So that is, there exists, let's use an a and a b in Z, where b not 0, such that root 2 is a over b. But now we're going to go one step further, and this is the trick to this proof if you want a trick. The thing to remember in this proof here is that we're going to assume that not only have I gotten written as a fraction, but that I've also got it written as a fraction in lowest form. In other words, this fraction cannot be simplified more. So with the GCD of a and b is 1. Okay? That's going to be the trick we're going to use here, is that we're going to require that the GCD of a and b is 1. Hey everybody, let's take a break from the example for a sec. The example I'm doing here is really just a single example, and there are literally infinitely more problems you can run into on a discrete math exam. And odds are good you'll run into problems you've never seen before and be expected to apply what you know to solving them. But if you don't understand the content, you have no hope. So if you're taking a university, if you're a student taking a university discrete math course, and you're serious about not just getting a good grade, of course, yes, getting a good grade, but if you're serious about understanding the content, then go ahead and click the first link in the description down below and book a free call with me. Now, back to the example. Okay. Now, from that point on, we got a lot of ugly algebra. First thing I can do is I can square both sides. So I get 2 is equal to a squared over b squared. Let's multiply by b squared, and we get 2b squared is equal to a squared. Now look what I've got here. I've got 2 times b squared equals a squared. Now b is an integer, so this is an integer. B squared is certainly an integer. So I have 2 times an integer equals a squared. Thus, 2 times an integer equals a squared, thus 2 divides a squared. Right? That's the definition of what it means for something to divide a squared. There is an integer here, so that 2 times that integer is equal to a squared. Now, but from that, look what I've got. A squared is a times a, and 2 is prime. And so what I can conclude now is that I've got a prime number dividing a times a. Well, if you look back, the theorem we have is that if a prime divides a times b, then it must have been the prime divided either a or b. Well, here I've got the prime divides a squared, a times a. So the prime divides a, or the prime divides a. Thus, the prime divides a. See how that works? Hey guys, if you are looking for help with learning discrete math or proofs, I know they're tough, then make sure to subscribe, as I'm literally going to be posting every example I have here for free on YouTube to help you learn and understand discrete math proofs. Back to the example. Think about it this way: if 2 didn't divide a, if a was not even, then when you square it, certainly you can't end up with an even number. Okay, and that's required that 2 is prime here. If this was a 6, 6 would divide a squared. Well, in fact, it would. But if 6 divides a and 6 divides b, or if 6 divides a times b, then 6 does not have to divide a and 6 does not have to divide b. Right? Because it's a prime number, we can do this. So thus 2 divides a squared, and so 2 divides a. Then, now I'll apply the definition of that. That means there exists, I'll use a k here, in Z, such that 2k equals a. That's the definition of what it means to divide a. And so, now I'm going to take that and replace the a with it. 2b squared equals 2k all squared. Let's square that out. 2b squared is equal to 4k squared, and divide by 2 on both sides, and I get b squared is 2k squared. basic algebra there. Now, b squared is equal to 2k squared. I'm going to apply the exact same argument I just did. 2 times an integer equals b squared. Thus, 2 divides b squared. And so, 2 divides b, the exact same argument I just did. 2 times an integer equals b squared. Therefore, 2 divides b squared. That's the definition. But then, applying the theorem we did before, 2 divides b times b. Therefore, 2 divides b, or 2 divides b. 2 divides b. All right, so 2 divides b. We're actually done now. Now, if you've lost track of where we're going, remember what we were trying to do. We assumed root 2 was rational. That is, you could write it in this form. And this is the point we needed this. The GCD of a and b is 1. Look what I've got now. 2 divides a, and 2 divides b. Problem. The GCD is supposed to be 1. But then 2 is a common divisor of a and b. And so the GCD of a and b must be greater than or equal to 2. And of course, the GCD was assumed to be 1. 1 is greater than or equal to 2, a contradiction. Thus, root 2 is irrational. That's it. It's a beautiful proof due to Euclid. Beautiful proof to show that root 2 is irrational. And what it turns out is that there are actually way more irrational numbers than there are rational numbers. We'll talk about that later. So yeah, hope you enjoyed that. Have a good one. We'll talk to you again. Hey, thanks for watching. Remember, what I've explained here is just a tiny, tiny example in the literally infinite space of problems there could be that you'd run into. So if you're interested in really understanding this content, getting a good grade because you understand the content, go ahead and click the first link down below and book a free call with me, and let's talk about if I can actually help you do well in this course.